Hello and welcome. My name's Michael Snow, and I'm here to talk to you today about the electrification of RMIT University. So, specifically, the major system testing that was completed across the entire portfolio, or the large users across the portfolio, and then the first implementation, which happened at RMIT Building 80, which is Swanston Academic Building. So, in terms of gas use on site, we're talking about the scope one emissions here, really quantifying what it all means. Electrification of the building stock for RMIT is about shifting those scope one emissions to scope two emissions. Scope two emissions would be addressed with power PPAs, but at the same time, it's important to consider the other options. So we considered what a hydrogen solution might look like, generating hydrogen on site with renewable electricities, biomethane options. They were considered but deemed unsuitable. Looking at the scale of the challenge to RMIT, in terms of the portfolio, there was over 350 assets that consume gas, boilers and general domestic hot water systems. 25 of these consumed about 70% of the total gas use. So it was categorized into major assets and then residual assets. So major assets were targeted replacement. The residual assets we'll address them over time as they failed and through various life cycle programs.
And that brings me to some of the challenges that this project had, and I'll talk to those at a high level. So we're talking across the whole university portfolio. There was a lack of data. There was quite a bit of data available, and I would suggest that the systems were better than most. However, there were some impacts associated with COVID and different utilization profiles that needed to be worked around and resulted in definitely an imperfect data profile. There's also undocumented organic growth that had occurred over the 3 centuries of the university's property portfolio. So the central city campus includes buildings that date back to the late 1800s, and those needed to be included. And over the many years, many refurbishments and refits, there is quite a bit of undocumented growth that has occurred that needed to be accommodated. There was also some real technical incompatibilities, real constraints in terms of how much space was available, electrical capacity, structural capacity, and specifically with heat pumps, the heating hot water temperatures, both the flow temperature and the return temperature, the temperature delta that we needed to work with for an optimized solution. And when you consider the number of installations that have been completed recently in our local market, this was going to be the first. So there was an immature industry for the retrofit market. There've been a number of new builds that had been built with heat pumps, quite a different approach because you can design everything the way it needs to be. We were dealing with an immature retrofit industry, and that needed to be considered very carefully in both the approach and the procurement methodologies, which brings me to risk apportionment, and that was quite important. When completing some of these, this work, we were going to be implementing introducing, I should say, a number of new risks that were difficult to quantify, and we needed to ensure that those and the apportionment of those were appropriately managed. As an example, in some cases, as much as you might want to outsource some of that risk to the contractor, need to give some thought as to, are they actually best placed to own that risk in the delivery? I think you find in some of these new and innovative spaces that may not be the case, and certainly wasn't at the RMIT site. We also had a number of sensitive stakeholders and stakeholder areas. We had normal office hours. We had 24-hour critical laboratory areas that had animal husbandry, among other sensitive activities going on. So actually getting a good understanding as to where our stakeholders are, what their sensitivities are, and how to manage those during any of our works were a number of the challenges we had to work through.
So first thing we did was consider the loads that would give us material benefit. We looked at it, and considering just 3 of the boiler houses, if we retrofitted just those, we would get the lion's share in terms of the emission savings. So that's where bang for the buck was, and they were selected as priority. There were known space and structural constraints and electrical constraints, and accordingly, for all of these locations, rationalizing the size requirement for the heat pump installation was deemed as one of the most critical. So first thing we needed to do was test for temperatures. Heat pumps, as you know, don't like responding at 80 degrees with 20-degree delta on the flow temperature. So we wanted to try and rationalize that if possible to open up our design options for the different heat pumps that were commercially available. So we looked at building 80 in the city, the city central thermal loop, which addresses most of the buildings in the main city campus, and the Bundura central thermal loop as well. So temperature testing, the approach, we called it stress testing of the portfolio to see what our real world capacity was. It's very difficult to define that based on a desktop analysis because there's so much diversity and literally thousands of FCUs that we need to consider. So it was a complex system. We needed automated contingency. So we had to consider that in the design of the testing. If anything was going wrong in the testing, by the time we found out that something was going wrong, there would be an inability to recover within a reasonable time frame. So if we dropped the temperatures, we needed to monitor those actively and have automated recovery in the event things were going awry. We needed additional consideration for critical areas, labs, artifact collections like the archives. They had tight temperature and humidity control, so a heightened focus. I've already mentioned very highly sensitive stakeholders. It's our users, but also we had a number of test facilities that had a number of even more sensitive conditions that were required. We ended up introducing effectively an algorithm that sat in our BMS, and that looked at valve positions, and it was able to basically isolate where valves were opening to 100%, and that tells us where we've got large portions of valve opening to 100%, we've got capacity issues. Now this is important because we had to design and develop these pages. Most BMSs have the ability to understand where their valves are, but nobody really has pages pulled together to sort of look at that. And so you'll see we in the bottom corner there, that's the temperature profile when we started testing. So we'd turn it on, and we'd find certain areas that were problematic. We'd make some slight changes, and it would sort of fluctuate up and down. And once we got a handle on what was happening, you'll see at the end there, we were able to refine those changes and step down through those temperature set points and maintain that lower temperature set point. So just to go through a few of the testing outcomes, the city plant, city central campus facility, that was an 80-degree starting temperature by design, and it had 20-degree temperature delta. We were able to turn that temperature down to about 55 degrees, and that was operated over the entirety of winter. The actual gas use, due to the lower losses through the extensive network of pipework, was also evident in the data as well. There was about a 10% reduction in gas use just associated with reducing that temperature. The system did operate very stably at this temperature throughout the whole of winter. All downstream appliances were unaffected. We did not see a material increase in complaints, but we did need additional boiler controls to enable resets and contingency planning in the event there was concerns. We did also develop a dynamic model so that we could troubleshoot any capacities, and the dynamic model looked at all the various pipe network flows, so we could see if there was a complaint in an area, if we were able to adjust in a fairly dynamic manner. The Bundoora Central Plant, that started at 80 degrees as well, and we did find a previously unidentified domestic hot water calorifier. So as soon as the temperature went down, we found that, and were able to isolate that from the testing program. But we maintained 65 degrees to ensure that there were no concerns with the domestic hot water storage in that area. So it's no longer a concern. That was refit to a heat pump for the domestic hot water during the last summer. So testing down to lower temperatures is now possible. Return temperatures were generally 10 to 20 degrees and not, 10 to 15 degrees and not lower, and not 20 degrees as designed. And Swanston Academic Building, which is SAB, that had a 70-degree starting temperature. It's a simpler building, standalone heating system, far less critical thermal requirements, but it did still use a large portion of the portfolio's gas. Um, it had it had a fairly complex control system already built in, and we didn't need automated aborts. There was plenty of existing alarms and complaint mechanisms. The existing condensing boiler had a 20-degree delta by design. We were able to run it down to 60 degrees with no increase in complaints or temperature concerns based on zone temperatures. And the return temperature was about 10 degrees throughout the testing that was completed. So once we'd done the testing, we did some rationalization of the results, and determined where we were going to go first. We chose RMIT Building 80, and we did that for space, access, complexity. We knew the existing building performance was appropriate, so double glazing, insulative performance, etc., and therefore the loads were likely to be rationalised to the best extent. It was connected to our district cooling network underneath Swanston Street, so we were able to get a fairly large cooling load, and we were able to do some simultaneous heating and cooling with a four pipe. And look, it's an iconic location for the portfolio. It's a comparatively low cost, installation. And the proof of concept to be done here was done in a way that could then be adopted across the entire portfolio with some good lessons learned. So first thing we did, looking at the capacity, that had 2.4 megawatts of heating capacity, and we're looking at the actual assessment. It yielded that it very rarely needed more than about 900 kilowatts. So these are some of the peak days. The very peak day was about 1200 kilowatts, or about the load of one of those boilers. But the peak loads were only a couple of hours a year. Generally, the assessment yielded that there were significantly higher heating capacity requirements than, installed capacity compliance than the requirements. And important when you're considering simultaneous heating and cooling is to understand where the load profiles occur relative to one another. You can see the heating, which is in the blue because it's cold, is the peak heating is about 1200, where if you look across to the cooling requirement, the peak is about 2.2, 2.3 megawatts. Why that's important is when you think about electrical capacity, which is a big concern, there's no simultaneous heating and cooling capacity in the building generally that would overlay an electrical requirement for simultaneous heating and cooling at the same time at significant capacity. So if you've got 2.3 megawatts of electrical equivalent for your cooling, you've got a large chunk of what you need for your heat pump during the winter when your chillers are not operating. generally speaking. Looking at the capacity, only 5% of the boiler operational hours were above 600 kilowatts. So that's another important one in terms of understanding the staging and the the sizing. So you can see on the graph there with the red lines, we went with two 600 kilowatts in the end, which basically provided full redundancy for the 95% of the year and the ability to service the peak for the entire year, with the exception of design days as an example, where the outdoor temperature is quite high, but also there's some defrost and some other things that are limiting the capacity of the heat pumps. So under those instances, we've elected in this case to maintain the boiler in situ, just in case. But the intent is that it will not be required in day-to-day use once we've been through a controls rationalization. In terms of other data that we used to determine I mentioned COVID was a bit of an anomaly, and understanding what the building loads look like relative to our different occupation patterns was very important. So you can see here, this is how many users attend the site. You can see that at a tertiary education, it's very distinct load patterns where there's semesters are on and off, and you can even see mid-semester breaks in there where a lot of people are not at campus. So understanding the time in the morning that people arrive for this particular site is also really important, because it gives you an understanding as to if there's any flexibility with your heating peak load requirements. So we looked at the technical options, and we tried to balance the implementation and operational risks with the technical outcome. The option was to retain the 70-degree flow temperature, and in order to do that, we could use a two-pipe system with air source or cascading, or we could look to reduce the flow temperature. And that opens up a lot more alternatives and also lower cost alternatives. So ultimately, we ended up going with a four-pipe air sourced unit, and that was due to the ability to simultaneously heat and cool, because we could access a large cooling load for the most of the year. And also there was that was a low weight and an acceptable electrical requirement to deliver that solution. So checks and balances in the design process. We followed a gated process to refine the design requirements well ahead of procurement, and we looked at feasibility. What will we need? Do you think we can do it? If you remember, we're very immature, so there was none of these systems that we could have a look at and see were they operating as designed. So we had to do some testing. Concept design. So we knew our needs. We had some constraints. How should we do it? And that's where we came up with some of the early rationalizations, and then through schematic and detailed design. Ultimately, this was let as a design and construct, and delivered by a contractor. The final selection was 2 by 600 kilowatt four pipes. We looked at four would exactly correlate with the existing boiler capacity. There was some concern if we reduce that, there would be an elevated risk. And the reason we went with 2 in the first instance, we've designed the system to accommodate 4 overall in the event that it's needed, but 4 would have required an electrical upgrade. And based on the loads that we've seen, 2 will be sufficient, and that peak can be trimmed with some design upgrades, or not upgrades, I'm sorry, some design modifications. So as an example, start the building a little bit earlier on those peak days. So we've got the capacity there, and everything is built in to accommodate the mechanical connection of additional units if we wish, but we would need to run an electrical upgrade, which we did not do. And in order to address that, we've left the boilers in situ, and the design does contemplate removal. And as part of the reasons for that is, we did test and it did reveal that it was okay, but we couldn't test to the worst case. It wasn't possible to emulate a design day. We are aware that the technology is immature and the capabilities are immature locally. And for this particular location, a lack or a shortage of heating would have been untenable. So it's really just part of the risk mitigation to leave the boiler there and have that removed at some point in the future once we've demonstrated capability and made those control modifications using real operational data. In terms of procurement, you do need to be mindful of contractor experience during procurement. There's not been many of these done, actually, not many at all. So you need to apportion the risk quite fairly, and RMIT were very much aware of that. If you wanted to do a design and construct and have all of the risk associated with the delivery of that on the contractor, then it's going to be prohibitively costly. So there needed to be a reasonable rationalization of risk, and an understanding of where the carve outs were and who was responsible. We did the implementation over summer. Of course, you want to try and manage your implementations over summer and not over the winter months, if you can. And you want to include comprehensive tuning programs. So throughout defects liability period, you want to have performance requirements. You can't just set and forget with a commissioning diagram on practical completion. You need the controls to be constantly evaluated, especially in the first thermal cycle, 1 year, and optimized. Ideally, you want to have that program in place throughout the entire year. And the intent there is anytime the boiler comes on, starts to use gas, we need to have a look at the system and understand what we could do. Can we change some of the parameters to to push that staging time out? Can we start the system a little bit earlier so that the boiler doesn't need to come on when people are arriving? The implementation, so this is now done and operational, and this was the first major heat pump retrofit delivered in Melbourne CBD. Can't forget to bake it in though. I mentioned a program to go through all of the other assets. You need to build that into your portfolio lifecycle program. You need to have policies and standards that set the parameters for your systems. As an example, fan coil units, if you replace any, size them for appropriate temperature today, and then when you do put a heat pump in at a lower temperature, there's no concerns. Build that in with master planning, understand how things are going to evolve and where you should put things, and then don't forget your energy procurement, of course. So in summary, you need to make sure you set your priorities across your whole portfolio, and you need to be mindful of your known constraints. Stress test your high priority sites, define what your unknown constraints are. But then you refine your priorities and you plan for implementation. For chosen locations, you need to look at your capacity requirements, and that's the capacity in terms of loading for the thermal loads, based on as much historical data as possible. Devise strategies to deliver electrification requirements, and that might include some thermal storage, like the RMIT example has, other controls, or hybrid implementation where you leave the boiler like RMIT did. And then, when you're developing your design, you need to continually test your assumptions. This is not something that you can generally refer to other locations in your portfolio for validation of those assumptions. When you do choose your procurement model, be very mindful of risk apportionment, and do include extensive performance validation requirements as part of your procurement. So the first three steps you should take as a building owner or a portfolio manager in planning your electrification would really be mapping out your assets that consume gas and understanding how those assets fit within a standard building life cycle. So are the assets new and inefficient, or are they close to the time that they would be replaced? Second is start to plan the testing for those assets that you think are near replacement, or your high value assets that you might have some tenants that are requesting electrification. You start to plan some testing for those buildings to understand where the limits are. And the third would be start to consider which parts of your portfolio have the highest risk. And what I mean by that, it's not just the implementation risk, it's also the risk of not electrifying. So there's a number of reporting requirements, but there's also a number of fairly critical tenant requirements that will be coming, and electrification of an asset will take likely a number of years to work through. So you want to have a good understanding of what's the risk of not electrifying various assets through my portfolio. You want to have an understanding of that ahead of time. So thinking about the testing that was done through RMIT's portfolio, uh, it did take a significant amount of time, but it's the time it would take is based on the risk of the site. So if you've got a very low risk site, it may only take a week. You might drop the temperatures and go, it worked, great. I'm going to go ahead on that basis. The RMIT one I planned over an entire winter. And we basically dropped the temperatures bit by bit, and we had a very critical review of the system's performance on the way through. So again, it's dependent upon the risk that's associated with your portfolio, how long it might take, and I think at the end of the day, the more testing, the better, if you can manage that. But do be aware that you need to do this testing during the coldest parts of winter. To ensure you get valid results, there's no point doing it in spring. You need to get get the outcomes during those really cold mornings. So I think in terms of the implementation of this project, look, it is quite complex in nature, but there are certain parts you could definitely do as a building owner yourself, and start the process before you started going to engineering design. Testing, as an example, that really just requires an understanding of the facility's risk, and mapping out I guess a risk weighted uh, set of steps that you would need to go through. So that could be done without complex engineering involvement. At that point, you could then understand, well, hey, this actually might be relatively straightforward. I've done some temperature testing. My portfolio is quite resilient in terms of temperature stress testing. I can now, start to look at the next step. So I think there is quite a bit you can do before you get detailed engineering involved, but it is quite complex, and you do need to think about who needs to be involved in the testing, and how you're going to keep a hold on the building conditions during that time.